This is Marius, he's my Newton's Cradle, and he's made up from some low-hanging balls on long strings, and he's actually pretty interesting. So I'm going to explain to you how he works and show off some of his cool tricks. Let's first get a demo. One ball. Nice. Two balls. I call this the 3-2 split. One from each side. I mean, there's loads of patterns. Let's go for another one. Let's go for 2 and 1. Very nice. And finally, my favourite is the gallopy gallopy. Love it. So as you can see, Marius is very talented. So what's going on here? Well, in physics, it's what we call an elastic collision. It's like when two snooker balls hit and the one hits into the other and the other one goes flying. Or if you've got two coins that are the same and you flick one into the other one will go moving. That's what's happening here. So basically, it comes down to two things in an elastic collision. There's energy and there's momentum. And both these things are conserved. So first of all, let's look at energy. Energy, in this case, could be like gravitational energy. So if I have gravitational energy, it could be like lifting this pen up. I'm giving it more and more gravitational energy. And if I let it go, that gravitational energy turns into kinetic energy or movement energy. So this ball, I'm going to give it gravitational potential energy by lifting it up. When I let it go, it's going to swing down and all that gravitational energy will turn into kinetic energy, which will then get passed into this ball, into this ball, into this ball, into this ball. The kinetic energy here will move because there's no ball to pass it into until it gets to its highest point. It can't go any further. All that kinetic energy is turned back into gravitational energy, and then the gravitational energy turns back into kinetic energy the other way, and it keeps going. Okay, now it's worth noting that this ball can never go any higher than this ball was dropped, because energy will not be gained from anywhere. Energy can only be lost in this system actually, and energy will be lost, and so this ball will actually go a bit lower than this ball, but it does go on for quite a long time. The other thing that's conserved is momentum, and momentum is made up from mass, which is kilograms. It's basically what we think of as weight, and velocity, which is like a fancy speed. It's like speed but with a direction. It's got no speed, so it's got no momentum. It's got a mass but no speed. Now as it accelerates down to this point, it gains momentum. Once it gets to this point, it also passes all its momentum onto the next ball, which passes all its momentum onto the next ball, onto the next ball, onto the next ball. This momentum goes up until it reaches 0, and then because of its gravitational energy, it's going to accelerate downwards, causing it to have momentum in the other direction. So an elastic collision has two things conserved: kinetic energy and momentum. Now this is not a perfectly elastic collision because energy will be lost, and it's lost through things like air friction. But even if you did this in a vacuum with no air, it would still run out of steam eventually, because there's also friction in the strings, and there's also actually frictions in the balls themselves. Even though they're made of metal, it doesn't look like they kind of squish in at all. They do actually squish a tiny bit. They compress slightly, a tiny fraction of a millimeter, and this compression will move the atoms to cause friction within the balls, and that will create heat energy as well, which is lost, as well as the sound energy, which gets lost to the surroundings. So as it goes on, energy is lost in lots of ways. Another question that gets discussed a lot with the Newton's Cradle is why, when you pick up two balls, do two balls come out the other side? Why not just one ball a lot faster? Or why not all three balls but not as much? Why is it that when I let go of this, two balls come out the other side? Now, it's a really good question, and there is actually a lot of complex physics to answer that. But there's also a kind of simpler way to think of it. Now, to summarize an elastic collision, basically what's happening is that one ball is exchanging its velocity with the next one. It's exchanging its velocity with the next one, right? Now, when we're thinking of two balls, we've got to think of them hitting at slightly different times. Now, imagine the gap is actually a tiny bit between them. They're not hitting at exactly the same time. This first ball is hitting a tiny fraction of a second before this second ball. And that means that the first ball passes its velocity to this ball, and to this ball, making that go up. And straight away after that first ball hit, this ball passed its velocity to this one, and to this one, which meant that one went up just behind it. Then they go back and do the same. This ball passes it to this ball, to this ball, to this ball, and the back ball passes it to this ball, and this ball. And they both come out, and you get that pattern. And the same thing works for when you've got two on each side. It's basically like these two balls on this side are exchanging their velocity with these two balls on this side. And at the same time, these two balls exchange their velocity with these two balls. And it works for any of these patterns. Even this 3-2 one that I showed before. It's really cool, this one, because you can see the middle ball, it's just kind of doing a normal pendulum. And it's as if the two balls on either side are exchanging their velocity with the other two balls. These two balls are exchanging it with these two balls. And it works with three balls as well. If I was to lift three balls up, you end up getting a pattern that looks like this. And think of it. This first ball is hitting this ball, which is hitting this ball. Then the second ball hits this ball and this ball. And the third ball hits this ball and this ball. And so you end up with three balls going out that way, and then you'll end up with three balls going back that way. So for this experiment, Marius has let me tape his two balls together, which I don't think he was best pleased about. It's just with some duct tape, so it could be nasty when you're taking that off at the end. And we're going to see how that affects the experiment. So you see, just by taping these two balls, we don't have two balls coming out nicely together on the other side anymore, and the pattern collapses in on itself much quicker. Again. So yeah, so if we join any balls together in this, it's going to considerably affect how the Newton's cradle works. So hopefully that explains it a bit. If you've got any comments or questions or suggestions, then please post them below. Thanks for watching, and if you want to see more of this, I'll post up some videos of some different patterns and some slow-mos for you as well.